But thank you everyone for joining. We're going to be doing a session on some API tips and tricks from ZIO. So we'll look at a couple of kind of sometimes maybe funny things that ZIO does, and we'll look at why ZIO does them and maybe why they're actually patterns that you could use in your code. And then 2 weeks from now, we've got a special panel that we're going to be doing. I think probably a lot of you are aware one of the big things going on in the broader Scala ecosystem is akka is moving from a open source to closed source model. I think that's making a lot of people reconsider what they're doing. And so we want to have some resources for that. I think next week we'll have some content from Kid and I on that. Then the following week, we're going to have a panel where I think John's going to join. We're going to get a bunch of people who've migrated from akka to ZIO in the past, talk about their experience there. And then I think after that, Kid and I are probably going to do a series where we try to migrate some kind of app from akka to ZIO. So a lot of good stuff coming there to kind of support folks as they're thinking about what to do there. But for today, we have fun API stuff.
So yeah, we just have the beginnings of a sketch to sort of, the static version of a slideshow, I suppose, to prompt us where to go. So we're going to be looking at a few different classes of techniques, a few different categories, and just going to walk through them, exploring first, as Adam said, a usage in ZIO, talk about why, like the motivation behind this trick, and then the sort of potentially ugly innards of the trick itself. One of like a meta technique, I guess, of library and API design is to bear the burden yourself of awkwardness in code as the library maintainer. Maybe it's not fun, but it's a very generous thing. If you can deal with the ugly tricks, write maybe some more code, you can expose a really nice API to your end users and increase their quality of life by taking on some awkwardness yourself. So that is kind of a pattern. You don't necessarily, this isn't the most beautiful code to write necessarily, but it does enable positive experiences for the consumer of the API. So it's just always about how to make it nicer for the end user. Cool. And we could also talk about, one day naming methods and consistency, because that's something we spent a lot of. We have a few different Google Docs and Google spreadsheets analyzing the uses of all our names, all the methods across the ZIO code base to try to make them consistent. But that's less code based. So let's get into it. So the first technique, I remember when I first saw this in the ZIO code base, I had no idea what was happening. I was able to sort of reverse engineer it just by looking at different uses and piecing it together slowly. But basically, it's this thing called partial type application. Maybe that makes sense to you. Maybe that doesn't make sense. And we're going to look at first just what it allows us to do, and then get into how we're going to do it. So let's just look at this very simple, moderately simple ZIO application, quite contrived, where we have a yeller service, which is going to yell some message at the user, and it may or may not fail with a sore throat error, custom error type there, which doesn't really need to extend throwable actually. So let me delete that. Okay, so we have a yeller service, and then we have a live implementation of that yeller service that will indeed yell the message, uppercased to the console. Or if the message is too long, it will fail with a sore throat error. Quite contrived. There are many ways of consuming ZIO services, but we often create little accessors that can be useful in both tests or demos or just playing around with an API. Because once we have this service, we'll want to use an implementation of that service, but we don't necessarily care which one. We want to use it, and as long as we have an implementation of yeller in the environment, we can call its methods. So one way of writing this sort of code would be to say ZIO service with ZIO, which takes some kind of service, here yeller, as a type parameter, and then we give it a function that accepts that yeller. So generally we call underscore dot, because we're really just generally delegating to a single method of this server, and then we call yell on it. So sometimes you might see this written like this, either because you're using a ZIO macros library to automatically put these on the companion object, or you would sort of do this yourself. Yell message is a string equals, and then I'll just put that same line of code here in the companion object. So we often call these accessors, which is just a little convenient way of grabbing an instance of yeller out of the environment and delegating to it. So we get back a new ZIO effect that can only run as long as there's a yeller in the environment. So it adds that environmental dependency. And it's just going to pluck that yeller out of the environment and then call the yell method on it. So you can write this. And then when we have this, let me go here and try to run this application, first commenting out provide, and we're going to get an error saying that your effect requires a service that is not in the environment. Please provide a layer for the following type, yeller. So then we need to basically call .provide, giving it that yeller implementation that we made above. And now it will work, and we will yell, hello world. There it is. Let me also make my console font larger because it's been a little while and it's not big enough. There we go. Cool. And of course, if we give this a message that's too long, it should blow up. Oh, maybe not. Oh, why is it not failing? What have I done? If message.length is greater than 25. Oh, that's because I'm always calling yell with hello world. I wrote my accessor incorrectly. I was not using the message that I introduced there. Let's try this again, and now this will surely blow up. There we go. Sore throat error. Perfect. And I coincidentally just got a sore throat. Okay.
Oh, no.
So that's the concrete use case. We want to be able to write these accessor methods. And canonically, for organizational purposes, we generally put these on the companion object of the trait. But for now, we're just going to use this service with ZIO helper directly. So this is nice to write. It's sorry, Siri was just activated. No one call, please. Hopefully. Oh, Siri. That is a Siri. Okay, hopefully she pops soon. Okay, so okay, I think that was her last death throw. Okay, so service with ZIO yeller yell. So this is a pretty nice API, I would say, because we give it exactly what it needs, which is the type of service that we want to access in the environment, and then a method operating on that service. We sort of need, this is all necessary information. We need to define which service we're pulling out of the environment, and then what we want to do with that service. So this is nice and ideal. But if we command click into this service with ZIO, we're going to see something that looks maybe a little strange. So it's not a normal method. It returns this other class, which is kind of weird at first. Luckily, there is a nice comment that will explain how you're supposed to use this. There are some drawbacks, sometimes some trade-offs that we get, as with all things in programming, when using some of these tricks. And with the partially applied type trick, you sort of lose some readability if you're using sort of your implementation as documentation. So be sure, if you do use this trick, to leave a nice comment that actually explains how to use your method, because it sort of becomes slightly obfuscated. But let's step back from this implementation and just think about how we could write it ourselves, sort of naively. So let's make our own service with ZIO. And let's think about how we want to do this. So first, we need some type parameter, right? That's what we're passing in here, which is the service that we want to access. And then there's this argument, which is a function from that service, right? It's right here, that yeller service, yeller, which we're just turning into an underscore parameter, to some use of that, to some ZIO effect. So some ZIO effect of REA, perhaps. So really anything that you want. Of course, now that we have the R and the E and the A there, we're going to need to add these as type parameters as well. And now we can implement this. And we can sort of just say ZIO.service, grab that service out of the environment. And then we can call flatmap. And then with that service, we can call F on that service. So using it, and that's basically what what service with ZIO is doing under the hood, with some extra complication to make the API nicer. So far, I mean, that compiles. What's the problem? So let's try to use this instead of the built-in version, and we'll kind of see what the problem is, which is that this doesn't compile because we've provided the wrong number of type parameters. So if you write it sort of naively like this, well, because we want the user to really return any kind of ZIO effect in here that can fail with its own errors and have that affect the result type, we want to propagate those types along. We have to introduce type parameters. And once we do that, we need to write those here. So this yell is not adding any new environmental parameters. So we could say any there. It does have a sore throat error, and it returns unit. And now it compiles. Oh, and of course, we need a tag for our service. So we can just write that there. Okay, so that all works. So clearly, this is not as nice, I would argue, because all of this information, the any, the sore throat error, the unit, this is all inferable from whichever method we decide. And so what we want to do is not have to ascribe all of these types. We just want to ascribe the only type that is sort of necessary to determine what comes next. And that would sort of be why we call this the partially applied type technique, or why it's called that, because we wish to only apply some of the type parameters and not all of the type parameters. So we need to separate it into these two distinct stages. This can be similar to something else. In terms of partially applied methods, basically what we want to do is, if we imagine some kind of mapping function, something that would maybe take an A, let's just take a list of A's, and let's take a function for mapping that, so from A to B. Let's see this. What's this going to do? Okay, and then let's just call A's.map F. So we'll just make that nice and simple. Oop. And I'm going to say nums list 1, 2, 3. And then I'm going to, oops, let's bring that back so that compiles. And I'll say mapping function of nums. And then I might want to like multiply my numbers by 2 or something. Unfortunately, this does not compile because probably many of you know this, but maybe not everyone does. This could be. When you have multiple parameters and you have type parameters inside of them, when you have a multiple parameter list that involves some kind of type parameters, the types of these type variables do not become fixed, do not become inferred until the end of that argument list. So even though we're accepting a list of int here, and the compiler knows this is a list of int at this point, we cannot just sort of get autocomplete on our ints like this just yet. And if we wanted to write a function like this, we would have to explicitly annotate that this is an int. And we'd have to do something like this, which is not great. So maybe you don't know this trick, but I think maybe most people would, but if not, that's great. Because if you want to write a method like this and you're stuck, you're writing an API and you're stuck having to annotate these types here, it's a bit of a bummer. What you can do is you can use multiple parameter lists. One of the, I think, the most useful purposes for a multiple parameter list feature is this ability to leverage the type inference of prior parameter lists. So now that we've broken it up into 2 parameter lists, the type of A gets fixed here in that first parameter list, and it is now known as int. So it can be inferred and used from thereafter. So we can not have to, basically, at this point, we don't have to specify any types, and it can figure everything out. Results equals a list of int, right? And if I did _.to string, it would now know that it's a list of string, which is pretty great. And so this is basically it's a similar sort of problem, And the solution is to use basically partial application. First, we apply just the numbers to this function, which allows it to affix that type parameter of A. And then we can apply the second argument, which is this callback function, in which at which point we know that A is set to int or whatever it was inferred to in this first parameter list. So that kind of staged inference, parameter list by parameter list, left to right, you can take advantage of that to make your APIs less annoying to use. No one likes describing types when they can be inferred. So we want the compiler to work with us and help us out and give us autocomplete and not have to feed it information it should be able to figure out. So that's generally the purpose of this. But this one is different because it's purely with type parameters. Okay. So, and we need to provide one of these type parameters because it really, this service that we're plucking out of the environment, there's no value for that. We need to tell it that. We're not giving it a yeller. We're not giving it a list of yellers. We need to provide it a type no matter what, so it can use that to pull it out of the environment using its.
Yeah. Yeah. I think that might, in a way, be like the highest level thing of if you're thinking yourself, like, when would this pattern be useful to me? I think the first lesson from ZIO is people hate writing type parameters. Like they never want to write type parameters. And so anything you can do to get them to avoid having to write type parameters, you should do. But the second qualification of that is sometimes you really actually need the type parameter. So like if we go to the original ZIO service with ZIO from ZIO, like this whole service with thing is basically just saying like, pluck this service out of the environment. Well, if we don't tell it somehow, it's not going to have any idea to know what service to pluck out of the environment that way. The Scala compiler can't kind of work backwards here and be like, well, someone's calling yell and there's only one yell, which is on the yeller. So it must be on the yeller service. Maybe some other languages could do that, but in Scala, it's kind of got to work forward with inference. So it needs us to tell it that. And so when you put together, people hate specifying type parameters, and sometimes we need type parameters. The conclusion of that is, okay, we have to specify this one, but we want to specify as few type parameters as we possibly can. And so we need to specify the yeller, okay, but let's make sure we don't have to specify anything else. And if you ever have a situation like that, where you need one type parameter specified for some reason, but you have other type parameters floating around, this is the technique you can use to solve that.
Yes. And I should mention as well, I guess technically we could use, in this case, that's a similar trick of annotating maybe here, and it might be able to figure out everything. But I'd argue, and probably most of you would agree with me, that looks really awkward, and it's not something that we necessarily love to do. I'd say this is a little more natural in terms of idiomatic Scala that we write, which is you apply type parameters sometimes. It's never a great thing if you're sort of requiring the person to write something like this. This just feels, to me at least, the prettiest, the most aesthetically pleasing, though that's arguable. I'm curious if that'll work with this pattern. It might not. No, it seems to work as well. Okay, cool. So that will work with here as well. All right. Great. But I prefer that. So yes, let's actually see how we can accomplish this with our versions. Let me call this the zero version, or bad. Let's call that bad. So there's our bad version, and let's make a good version. Let's actually replace this. So let's just kind of go through what we want. What we want is just to have one type argument. And that's sort of a rule of Scala, is that if you do ascribe a type parameter like this in brackets, you need to provide all of them. So you can't just do one. So that means if we're going to write something like this, that can be the only type argument. And if we sort of look in the real implementation, we're going to see that, yes, there is only one type argument. And it seems like there's this other type involved, this other class involved. And that, yeah, we'll see what the heck that's about. So we just want one argument here, service, which means at this point, we're just limited, and we just follow these constraints. We just cannot write this right now. We can't take an R and an E and an A. Eventually we need to, but we can't do it yet. So what can we do? Well, let's make that question mark. So what we could do is we can define perhaps a class, some other type. Doesn't really matter. It could be a case class. It could be a trait. I think they generally end up being any val classes. we'll take a look at the real example. And then we make this new thing. And let me turn off Copilot so it doesn't help spoil all the fun. So we're going to call this service with ZIO partially applied. And then we're going to give to this a type parameter of service. So let's do this. So we're just going to make a new service with ZIO partially applied and put that type there. So we're basically creating this class that stores the name of this. It's keeping track of that one type for us, and only that one type for us, which is totally fine. And if we go back to see how we're using this, it seems that what we're doing, if this is returning a type, we're sort of calling it like it's a method. In fact, at the call site, it's not very clear that there is this additional type created in between, which is interesting. So in order to do that, whenever we call something that looks like it's just a method, actually what we're doing at any point is actually calling the apply method on that type. So there's a special syntactic feature of Scala where if you have a method called apply, another way of calling that is just by, well, calling the thing as though it were a function. So you don't have to write apply. It will, at compile time, expand that into calling the apply method. So if we want to obfuscate the fact that there's this intermediate class here, we can create an apply method on it. And the apply method here can take its own set of arguments. And so basically, this is where we can take this signature and shove it in here. So we can put the R, the E, and the A on this apply method. And now if we try our custom version, we'll see that it actually compiles. So that is enough for it to work. And let me run this. Oh yeah, we still need a tag here, which we can either we can require in different places, but for here, I'll just require it at the call site. It really doesn't matter much. Implicit tag of service. Here we go. It's compiling, and then we can run it, and it's going to say hello world. So that's basically the pattern. If we can solve the real ZIO real quick, we could see exactly what we're doing here. I'm pretty sure there's in order to sort of attempt to reduce or eliminate the overhead, the cost of creating this class, it does extend any val. So let's do that. And there's also some other stuff which we'll take a look at. So if we make this extend any val, which will theoretically attempt to remove the actual allocation there, we'll see that it's not happy. That's because it needs to have exactly one parameter, which explains why we have this dummy Boolean parameter that really isn't used. I don't think it needs to be a val, and we can make it private because that should never really escape. It's just there so that we can use any val and avoid allocations. And I think that's kind of the pattern. So whenever you're in the situation where you have a method that you're trying to write, and some of these type parameters should be inferable, but they can't all be, and at least one needs to be ascribed, then you can basically take that or however many parameters must be ascribed and create a class that has those as type arguments, and then move the actual implementation with the remaining arguments to an apply method on that. And basically rename the original method to only take those partially required type annotations, and then just instantiate that class in there. So this returns an instance of this class, which when called like a normal function, will sort of just, at the call site, you can't tell it's doing this crazy thing. It just looks like it's working nicely. Now, because this is manually writable, one would imagine that this could totally be done by the Scala compiler. So that would be a cool feature. Maybe it's a feature request we can make, because it certainly gets, like, as I mentioned, when you command click on this and you see something like this, if you're not familiar with this technique, though now we all will be, it can certainly be a bit disconcerting and a little harder to just read the code because you have to jump again before you can actually sort of figure out what's happening. But other than that, as long as you have this method very nicely documented, so we definitely want some good documentation here, good docs, then it really solved that problem quite elegantly. Yeah, I think it took a while before I realized that until I finally command clicked and realized what it actually was under the hood and got confused. Anyway,
Yeah.
great
And there are some potential improvements coming in Scala 3, and maybe we can do that in another session at some point. But at least a lot of people, if you're like writing the stuff that needs to support multiple versions, or if you're not on that yet, this is something that will kind of get you through no matter what version you're on. So it's nice that way.
Oh, interesting. I'm not sure what is it like generally the feature skull through.
You can kind of have like there's at least some stuff in process to be able to have multiple like type parameter lists.
Oh, okay. A multiple type parameter list is exactly what we need then. Okay, yeah, I wasn't sure that was coming. Cool.
Well,
That'll make it even nicer. But until then, if you want to have this trick in Scala 2, there you go. That's how it works. Do we have any questions about that?
So we had one question, I don't think a little bit less about the pattern than about this usage of kind of these like accessors and like when to define accessors. And I think it's a really good question because there's a little bit of a change there between ZIO1 and ZIO2. I think in ZIO2, we've a lot of times actually moved away from needing to define those accessors because if you do a fully idiomatic ZIO app architecture, and I think you can go back to one of the other symposiums that we did where we kind of showed this. What you end up having is you call each is you implement higher level services in terms of lower level services, and you actually call each of those lower level services just in the implementation. You actually have access to that service. You don't need the accessors. So where that accessor ends up being more used is potentially in test code. It can be nice to have in your test code, at least if you're calling something a lot, or if your main app isn't itself a layer. If your main app is a layer, then you actually never need to do it outside of your test code. So yeah, there's definitely less need for these accessors, but still sometimes come up. So definitely good to kind of know. And yeah, I think part of we just selected this is an example of this technique. It can definitely be useful in other places.
It sounds like I've jinxed us. We both have sore throat errors. No. But yeah, so I was trying to sketch out a very basic idea of what you were just saying, which is that most of your application will be services comprised of other services. And so because we're accepting an instance of the service as an argument here, we're not going to have to say, we should never say ZIO dot service yeller or service with ZIO yeller here to access that from the environment. Instead, we're just going to use the one that we've accepted here, which is going to be propagated along and constructed with our sort of our main layer. Though, as Adam mentioned, when you're testing, it can be sometimes convenient, or if you're just messing around, like I am down here, it can sometimes be convenient to have service with ZIO. Pardon me. So that's nice. But yeah, I think maybe we should do something about that in terms of like calling your application at the very top level sometime. I think we talked about that in the architecture symposium we did a while ago.
Yeah.
Maybe it's worth revisiting at some point. Cool. Well, with that, cool. That took us. Our probably went a little too in depth. It's a little rambling. My brain's booting up.
I feel like we always take a little longer than we think we will.
Yeah, but it's good. It's good.
It's good. It's definitely good. It's definitely good.
Got some details and tangents. I appreciate it. And we got a good group today as well. So okay,
Yeah.
trick number 2, a little simpler. Should go by a little faster. Is implicit evidence. Well, I guess maybe not, because we have 3 sort of different varieties of implicit evidence that we want to talk about. But the overall technique is this one of requiring implicit evidence. And we're going to sort of look at a few different concrete uses of it. So one would be defining methods only on specific subtypes of a DSL. So in the case of ZIO, that DSL is going to be ZIO itself. So we could take a little example here and look at this. So here I have this optional string ZIO. So it's just a ZIO of an option of a string. And I want to call this method on it called sum or fail exception, which if I pull this out into its own ZIO type, we'll see that the option of string, so previously this couldn't fail, the IO of option string becomes an IO of an error in a string. So it basically moves the none case to the error channel, failing with no such element exception if it is a none. Otherwise, we just get to use the string. So if I debug this and say results, we'll see that we indeed get hello. And if I turn this into option.empty, we'll see that we get a no such element exception. Oh, it's very sad. So let me undo that and go with the hello case. So that's nice and all. That has nothing to do with what we're talking about yet, sort of, I guess. But how were we able to call some or fail exception on this ZIO? It really doesn't make sense unless the ZIO had an option as its return type. For instance, on the string ZIO, it cannot be none. And in fact, this code won't even compile, which is very nice. And it gives us this error that says this operator requires that the output type be a subtype of option of B, but the actual type was string. So we get that helpful error message as well, which is pretty nice. And so there's this technique of implicit evidence, which allows us to do this very sort of thing, which is what is here, define methods that only make sense for specific subtypes of a DSL, whether that means that the output type needs to be a specific subtype, so it needs to be a subtype of option, or perhaps the error needs to be of a specific type, or the environment contains specific types. This is a trick that allows you to operate, add methods that only compile on those certain subtypes. So this is one example. So this will only compile on option string ZIO. And furthermore, it allows us to implement it in a way that makes sense without casting. So let's see how this is implemented. So there's a bit of noise here, but let us see what this is. Really what we want to pay attention to so far is this bit here, which is that A is subtype of output option B. So this means that the A, which is that if I scroll all the way to the top of ZIO, all the way, which is the success type, the output type. We have the R, the environment, the E, the error, and the A, the success. It basically says that the A must be a subtype of option of B. And if that is the case, we get this little implicit constraint of this weird looking type sentence. And this is a value. And if we look at where we're using this value, well, we're using it on the A. So this set in fold ZIO, we get to handle both the failure and the success. And so we're taking the success value. It could probably just be A arrow here, but we're being a little terser. And so we're calling this evidence on the A, which actually turns it into an option of B. So not only are we ensuring this implicit evidence will only be found if A isn't a subtype of option of B, but then this doubles as sort of a usable piece of evidence where we can, now that we've proven that using implicits, we can call it on our A and it will actually turn that A into an option of B. And then we can match on it because it is an option of B at this point. The value is of type B and we can use it from that point on, which is pretty nice. Now this is subtype of output is sort of one layer beyond the base technique here. And this exists mostly to give us nice error messages and a little bit more description here of what our intentions are. The default way of using this technique, the way that you'll see in more standard Scala libraries, is this operator here, which if you don't know what it means, can be a little confusing. At least this one tries to give you a clue, tries to be somewhat readable as a sentence. Okay. So yeah, but if you wanted to read this, you could read this as is a subtype of. So no such element must be a subtype of E1, or you could read it as E1 must be a supertype of no such element exception. Is that correct? Yes, sort of. So it's a bit complicated. Let's maybe back away and try to write this ourselves with a simpler example so we can get an idea of how this all works. So let's make ourselves a box. So a box is just going to contain a value. And let us call a method on this called get. And we want this to only make sense if the box contains an option. And then we will basically forcefully unwrap the option in the box. I could do get or else default or whatever, but just to keep it very simple, we will call get on this. So what we want to do here is basically say implicit evidence that A has to be a subtype of option of some other type. So we're going to have to introduce some other type, which we can call B. And then what we can do is basically use this evidence as a function on our value. And we can see right away this turns the A into an option of B. That's our new result type. But we can also mash on it at this point. And or we could call it, I guess, get, which is the purpose of this. So we're going to call get on that. So this will get us out a type of B. So now we can use this object box example, val box of option of hello. And then I can say box dot get. Oh, box option dot get val result. So this is a box of an option of string. And now this is a box of string. Or not just a string, rather. Let me make a similar version here. There we go. So now if I just do box of string, extends app, we're going to see that this doesn't compile. And it gives us this error message, which once again, if you don't know how to read this or know this pattern, it can be a little confusing. It's saying cannot prove that string is a subtype of option of string. Even though string is a subtype of option of string, or is not, sorry, even though, no, I don't know what I'm saying. String is definitely not a subtype of option of string. Okay, so let me go back to the box option. Box option. So in this case, option of string is a subtype of option of string because it's the same type. I could even make this, for instance, sum of string, and this should work. Because sum of string is a subtype of option of string. I could even make this a box of none. None. I guess none.type. And that's also going to work because none.type is a subtype of option of some other type. Obviously, this will blow up just due to our implementation, but it compiles. So A is the type of our box. So we can call this as long as A is a subtype of option. Simultaneously, we can use this evidence as a function to convert from A to option of B. In fact, we get the same behavior even if we just required the implicit evidence of a function from A to option of B. So maybe that's clear what's happening. I'm not sure. Let me make this option of string again and do option hello. Hello. So this still works. So maybe let's take 1 minute to think of how this is working, or to explore how this is working. So if I show implicit hints, and I think I've talked about this a little bit in the implicit hint section, we get this little thing here. It says refl, reflection. Where's that coming from? Well, is refl in here? Let's see. Refl. There it is. There's this implicit instance of this thing, which all looks crazy. And there's all of these signs and type theory and whatnot, and it's all pretty insane looking. And it has all these methods on it. And it's all pretty crazy. But we can see that this thing it's really just a class, an abstract class. So kind of a trait, essentially, that goes from something to something, and it basically extends a function from to. And it's supposed to mean that the left-hand side is a subtype of the right-hand side. But if that's all too crazy, we can sort of implement something like this ourselves. Trait is subtype of AB, sub soup. Maybe I could call it this.
Have you been watching The Boys?
The what?
Oh, there's this Amazon show called The Boys, where like the heroes are like soups. Yeah. Sorry, bad joke.
No. So widen now would be this function that took the subtype and returned the supertype. Great. So that's kind of this trait. And of course, we need to have an instance of this. So let's say implicit def, and I'll call it duh here, of some type A. And we can actually create an instance, new is subtype of, when it is itself. Right? A is a subtype of any A. Any A is a subtype of any other A. They're the same type, yes, but they're also subtypes. And now to implement widen, it's quite trivial. All we have to do is return the subtype, which is itself. Great. Lovely. So now if I go to this, I can actually say is subtype of our little custom thing here. Of course, now I have to call the widen method. If I wanted to, I can call this fly, and therefore I wouldn't need to do that. But for now, let's be very explicit. And also, there's that additional trick that if you have a 2-argument trait, you can write it in infix notation just because what the hell? Let's be very adaptable. It's the scalable part of the Scala language. Allows you to do all sorts of craziness. And we'll see that this actually works just the same. And now if I show implicit hints, let me print that actual result, we see that it found duh. And this should still work, I believe, even if I make this a sum of string. No, will not work, because I think I need to make this now covariant and contravariant in the right arguments, and then it will figure it out. Anyway, a bit of complexity. So what's really happening is when you have this implicit evidence, you're saying that you just want this function where basically A is the other side. You want to say that you know that A is this thing on the right, and you want to be able to write this function assuming that is true. And then the mechanics of it is you have this type class. It's a simple function that basically casts or widens the subtype of the supertype. And it's all powered by this implicit that basically takes some type A to itself, returning itself. And why this works even when the thing is a subtype, for instance, sum of string is a subtype of option of string, is because Scala will widen a subtype. You basically can use a subtype in the place of any supertype anywhere. So it's going to see that there's this instance duh here. It knows that you're trying to synthesize an instance from sum of string to option of string. And then it's going to say, well, hey, if I made this sum of string an option of string, then I could use this implicit instance. And it's going to allow that because this is contra and covariant, whatever. Doesn't really so much matter. But the point is, it's going to do all that crazy stuff for you behind the scenes. And at the end of the day, get you this value, which just proves an obvious thing, which is that something is a subtype of something else and allows you to call that. I'm not sure if I explained that very beautifully, but that's basically what's happening. Of course, the error message if this is missing can be very terrible. So box of string. So what we're going to get now is it's going to say something like, could not find implicit value for parameter f is subtype of. I guess that's a little better. But the last step that we did in ZIO2 is instead of using this built-in sort of method, this built-in type that comes with Scala that does this exact thing, which is now sad for some reason that I'm not, because that's a box option. Because we wanted to avoid the issue of box string of this error message, cannot prove that blah, which is unless you know exactly what this operator is, it can be very unreadable and confusing. It doesn't really guide you. Basically, we made our own version of this. So if I go back to sum or fail exception, it is subtype of output. We have a few variants of this, depending on if it's a subtype of the output or a subtype of the error, whatever we're trying to refine. And basically, there's this additional feature where if an implicit is not found, you can come up with a special error message. And so we basically just, it's essentially the same as what we just did with a little more complication. But really, the purpose of it is so that we can have a bespoke error message that applies to exactly the situation that we have. So hopefully it's a little more guiding than just this is smaller than this other thing, which is another example of doing some extra work on behalf of the end user. So it's just like a little nicety. But if I do have this here, and I go back to using is subtype of, and use my widen method here, and now if I run this and it's not finding the implicit error, it's going to say this operator required this output was a type of blank, but well, actually nothing's working because this implicit not found annotation is very wacky, and you have to have this like faux string interpolation thing. So these need to align with the parameter names. Now, if I run this, we should see. Oh, I got them backwards, but you get the idea. we can give a nicer error message. So that definitely took longer than I anticipated. It's pretty detailed. Basically, in your code, though, if you want to do this, you don't have to go through the whole rigmarole of making your own custom types. You basically just have to add some implicit evidence of going from the type that you have to the type that you want. And if it's even easier for you to remember, you can also just make that a function. Because this type is a subtype of function, it will work. Yeah, and that's basically that trick. One last addendum. There is another way of accomplishing the same thing with some trade-offs. For instance, if I go back to box option here, instead of doing this trick here, let me move box down. Instead of doing this trick here, you could also accomplish the same thing. Where's my implicit? Oh no, my shortcut's gone. I must have turned that off somewhere. Anyway, implicit class, box ops. Oh, well, I do need to be inside of an object.
Right.
So yep, that's probably why actually. It's being clever. There we go. Nice. So box ops for A. You could also create an implicit class that operates on that subtype. So I could say box ops of option of A, and basically copy this method, remove it from here, and then I can just operate on this. In fact, the implementation becomes maybe a little clearer because we don't have to do that casting. We're just writing a method on a box of option of A. Apparently though, I think maybe I need to make that covariance. I think this probably needs to be covariance for it to work with the sum of A. There we go. So now we'll see that it's just doing the same thing, but it's first instantiating a box ops of A. And with IntelliJ, we still get autocomplete for these values, which is cool. And if we try to call it on the wrong type, well, now it's a little different. Now it's just going to say get is not a member of box string because it's just simply not, the method just does not exist on a box anymore. It exists only when this implicit class fires because of the type of box you're trying to call the method on using implicit resolution. Check out the episode we did on implicits. So there's a bit of a trade-off here. One is that, well, you could say at some level, these methods that don't apply to box of string aren't polluting autocomplete. So you don't see get there, I guess that's possible. But at the same time, maybe you'll never know that get exists. Maybe you'll never know to look in implicit classes, or when you command click on the ZIO type and you look through the methods that are available to you, you just won't see it because it won't exist there. It'll exist in some implicit class elsewhere. I think in ZIO, we generally go for the first approach of using implicit evidence because implicit conversions are a little less discoverable, perhaps. But both, you have the same power with slightly, it's a matter of trade-offs. It depends on your example and your particular situation. I'm going to shut up for a moment. Or a few moments. Any additional thoughts, Adam, or qualifications, or any questions or anything?
Well, someone said seeing you write code was like watching a magician at work, which I said true story, especially with your little trick there to create the implicit class. So that was very nice. But no, I think that was a great description. I think you're exactly right about the trade-offs there. I think one thing you might think about is maybe is using this thing on the quote unquote like happy path. Because I think in ZIO 1, we had some cases where we did use more of the implicit classes for like things with layers. And because sometimes like, well, the layers only fit together, right? If like the types line up, but then that would result in situations where like they didn't quite line up and you just got, well, XYZ is not a method, which is not very helpful, much less helpful than getting the message saying like, well, this expects this to be a subtype of this, but it wasn't actually a subtype of this. So I think that's like a really great case for using the implicit evidence and putting it on the trait itself. I think maybe if you had something where like, maybe like in ZIO flow, they have like these remote types, right? And you have like remote numeric types and remote string types, and they all have different operators for the appropriate thing. Maybe that would point you a little bit more in the extension methods because you're like, look, there are going to be a lot of different operators on different types of remotes. And if all of them show up in autocomplete, maybe that's overwhelming versus, okay, if it's a remote of int, you get your int operators. If it's remote of string, you get your string operators. But I think you're right that in ZIO itself, we've moved more towards doing it through this implicit evidence technique.
Yeah. Someone did ask in the Zoom Q&A about any performance differences between the two techniques. I mean, I don't think it really matters. This one, I guess, uses any val. So if any val works as advertised, which it doesn't always, that might just get erased to just calling this, whereas this needs to call an additional function call, but it's probably very cheap anyway. I don't know if it matters. And the JIT will probably eradicate both anyway, hopefully if we're lucky. So I'm not, I'm not sure. Probably negligible. It's probably, yeah. I mean, if you're doing very low level stuff where you're afraid that this will matter, probably don't use any of it. And instead, just do low level ugly things at every other point in the code, though. Just figure out whichever one just like is more ergonomic and discoverable. And I think that's a great point. Yeah, it's like with the remote data types, it's kind of like this box, right? Where you're going to have a box of so many types, and you kind of want to forget, you want to remove, you don't have to like call map every time, and you want to be able to like access the box as though it were the value inside of it. So we can implement get on a box of option. We can implement all these list methods on a box of lists. And then would just, these implicit classes probably would just take care of doing some extra mapping through the container, and you can use autocomplete as you would with a normal list or option. So you won't get everything that exists on box, half of which or the majority of which you won't be able to call because you will not be able to synthesize the correct implicit evidence. So yeah, different cases call for different techniques, and it's all trade-offs. Technically, there are some instances in ZIO. I know on Z layer, we added a newer version of this pipe operator, which I'm not sure if many people use, but we tried to implement it on the Z layer itself, but it did not work there for mysterious reasons. So sometimes the general Scala rule is if you have something you want to try to get to compile and it's not working with one technique, use every possible combination of techniques that you have available to you until it finally maybe works if you're lucky. And it turns out that we were able to eventually implement a version where you can provide a partial, a bit of the layer. So if you had one layer that depended on A and B, we can now get it to type infer if you just apply a layer that provides the A, that the remainder is B. But that would only work if it's defined on an implicit class for whatever reason. So yeah, that's always another option for you. Okay, so there's that. Well, there were a couple of other examples, but I think we talked about the custom evidence with nicer errors. So that's the is subtype of. But there's this other flavor of implicit evidence which prevents sort of code that just isn't necessary to call, redundant code. So not necessarily code that only works in some case. You could still call it. It doesn't have any sort of, it's not only valid for particular subtypes of your DSL, but it's just not necessary for particular subtypes of your DSL. And in ZIO, an example of this would be error handling code. One of the greatest things about ZIO, in my humble opinion, is the error channel. And one of the best uses of the error channel is not really to sort of track typed errors, even though that can be totally fine. But the best part is that you can encode the fact that you have handled your errors. When the type is nothing, I find to be just the fact that you can distinguish between handled errors and remaining errors is very useful. And one way of taking advantage of that is, for instance, say we have this optional string ZIO, or let's make another one called booming ZIO. And I'll just say ZIO.fail, new error, a boom. So we have this ZIO that will never succeed and will fail with an error. Well, on this method, I might want to call booming ZIO or else succeed of hello. And I'll debug this. We'll hide implicit hints so we don't spoil anything. And we'll see that we get hello, great. But then what if we instead change this to succeed? Nice. So it's not booming anymore. Now it always succeeds. Well, we can see that the code we just wrote became non-compiling. And it's going to say that the error handling operation assumes your effect can fail. However, your effect has nothing for the error type, which means it cannot fail. So there's no need to handle the failure to find out which method you can use instead of this operation. Please let it short. So it's very nice to give it short.
That is going to give you a threat.
That is a good error message. So we also like take advantage of this to like teach you a little bit about how to use ZIO. And if people didn't understand about this error channel, now they're going to probably learn something more, that basically this can't fail. So this is totally not necessary. This will never run hello ever. That's guaranteed at the level of the compiler now. So we're simultaneously helping the user delete code and teaching them a little bit about how ZIO works. And so how does that work? Well, if I show implicit hints, we'll see, well, that there's actually an implicit error. So we're taking advantage again of this implicit not found version. Let's actually go back to the boom so we can see the actual success of this implicit being found. New error boom. So there's this can fail type, which is necessary for or else succeed. So all of our error handling methods require this can fail implicit evidence again. And what this is just another sort of this little marker trait that is implicitly resolved. And it doesn't really have any interesting value in and of itself. It's just there for the error message when it cannot be found. So how does this work? Adam, maybe you can walk through how this one works.
Yeah, definitely. So basically what we're saying here, we're using a little bit of this ambiguous implicit trick here. So the first thing we're saying here on line 31 is essentially anything can fail. So you give me a type and I will give you an instance of can fail for that type. You want to say an int can fail, and it can fail. You want to say a string can fail, a string can fail. Whatever you come up with, it can fail. But then what we do is we implement two more specific ones, which you see on line 41 and 42 here. And these, other than having the same name, are actually the same. And they're instances of can fail where the type nothing. And since this one's more specific than that general one we had on line 31, the Scala compiler is going to look for those if it's looking for an instance of can fail for nothing. And because there are two of them and they're of exactly equal priority, right? They're exactly as specific. They're in exactly the same object. There's not like one is extending the other. They're exactly the same priority. And so the implicit resolution Scala has this rule that basically says, well, if it's ambiguous, then it's not just going to arbitrarily pick one. It's going to blow up and it's going to say ambiguous implicits. And you may have probably inadvertently sometimes seen that error if you were relying on things that were supposed to be available implicitly, and maybe you had something that wasn't working quite right. So it's a little bit of you hack the Scala 2. In Scala 3, there's actually a little bit of a nicer way to do this because there's a not given that you can use. But since we want to support all versions, we have this on Scala 2, and then we have that not given for Scala 3. But what the upshot of all that is that if you ask for a can fail for any type except nothing, it's just going to give it to you from line 31. Then it's not going to say anything. And if you ask for a can fail of type nothing, it's going to blow up because it's ambiguous, and it's going to give you this lovely and also voluminous error message here. And if you want to even click through to the link, and I think we should see a nice table as long as we haven't screwed. Okay. No. So we got to update and our folks have been doing a lot of amazing work on improving the documentation, but I think we may have, let's see if we fix that. It's not made this version or we need to fix that, but that is a good to do for me. So I will do that immediately after this. But nevertheless, once we get the link working right, it'll take you to a nice table and it'll kind of show you like all the methods that you might call and what you would call instead of them. So like if you were going to do like fold ZIO on something that can't fail, well, the error case doesn't matter. So that would just be flat math, and it'd basically just have like each of those conversions for you.
Yeah, having links in the error messages is really nice. But the one downside is, there's nothing that's making sure they're up to date. We could probably write some kind of CI tool to throw errors if that is important.
Yeah, well, hopefully we can make some of those changes a one-time thing as we've been kind of upgrading here. But yeah.
So awesome. And basically, so yes, if the E is nothing here, which is how we signify that a ZIO cannot fail, then it will trigger that ambiguous implicit, which will give that nice error message. But if you're failing with any other type, it's cool. And that means in this concrete case that, well, if your E is not nothing, that means your ZIO effect can fail. So, but we can just see that right now. If I say like implicitly of can fail of string, that's happy, it finds can't fail. And really anything I put here, it's going to find, unless I say specifically nothing, in which case it cannot resolve it due to the fact that we provide too many instances. And then we override the ambiguous implicit error to give us something that obfuscates our hackery. Because it would be very confusing if it like says it couldn't find implicit value of something, because it's really just a trick. So yeah, all these tools are kind of just fun little, I don't know, coincidences, accidents, just due to the beauty and complexity and composability of Scala as a language. You can sort of outfit it with features that I don't think were ever really intended. I don't think this is what like Odersky was planning when he put these features in here for them to be used for this level of sort of API
Very.
slash hackery. But it's very cool. Uh, yeah, and it's great that in Install 3, some of these tricks have been sort of given a first class status. So that's the last one for implicit evidence. So a lot of interesting ways of using that. And then I think lastly, and we're getting sort of towards the end, it's up to you. We've been an hour. Like, do we want to save the rest of this for another time, or do we want to just check out the last one here?
I'm fine either way. Maybe we try to just do a little bit of a quicker review on this one.
Yeah, sounds good.
All right, awesome. Uh, so I think one of the things that you may have noticed if you've used ZO2 is there's a little bit of this new unsafe thing. And basically, what we're the problem we're trying to solve here is you may have an API where you've got some things that you kind of expect your users to do. So, like we've got some ref tray here, and then a common thing they might want to do is they might want to update the ref, or let's say let's just make it simple. Let's say they're going to want to set it with a value, and so we want to make all this referentially transparent here and describe what we're doing here. So we're going to make this return a ZIO, and we feel great, we feel wonderful about ourselves. But then someone comes along and they're like, well, this doesn't work for me because I need to update a ref in somewhere where I can't really use a ZIO. Maybe I am implementing a logger. And if you probably haven't worked with the low level logging interface in ZIO, but like the lowest level interface, it doesn't use ZIO workflows. It just does things because it's supposed to be very low level that way. You can imagine you would have a lot of other situations like that where maybe you're working with Tushar on ZIO HTTP and he's trying to do something very performance sensitive, very low level to make things fast. And you tell him, well, you got to have a ZIO effect to update the thing. And he's like, that doesn't work. Eh? So in ZIO1, what we would do kind of if we like really needed it is you'd have something like you will say, okay, I'm going to have unsafe set here. And this is going to be like the unsafe version of this thing. And sometimes we would kind of try to prevent people from using it outside of like ZIO libraries that needed to internally. And we would do this like private ZIO thing. Though then sometimes that didn't work because you could imagine you have a library like Caliban or others that are part of the ZIO ecosystem, but aren't actually in the ZIO namespace that maybe they need to use this thing. And then this thing doesn't work. So yeah, I think this was an okay convention here of just putting the unsafe in front of things. It definitely makes it very in your face that there's something going on here that you should be careful of. But I think you could also say for this that we're not really getting the compiler to help us out at all. Like if we want to, if we say, hey, we really don't want to use this, even though it's in the API somewhere, we really don't want to use this. There's no way you can enforce that other than like you look at the commits of the PRs people do and you say, oh, you're not supposed to do this. You're not supposed to do this. Or maybe you can kind of set up some like linting tool to watch for some of these, but I find a lot of times those are like hard because maybe there is like a particular case where like you do want to do it and it's kind of hard to sometimes incorporate that with the linting tools. So what we started to do with ZO2 is we moved to a little bit of this pattern where so what we'll do here is we'll have some additional trait inside here and a little bit just by convention what we'll call it. A lot of times we'll call it unsafe API. And then the set gets moved inside here. And then it doesn't need the unsafe in front of it because it's inside the unsafe API. And then we just have some little method here that just gives you the unsafe API. And so in this world, if you wanted to do something unsafely with your ref, right? Say, well, we've got this ref int, that's something. and you wanted to do it unsafely, instead of in the old world, you would do something like ref.unsafe set to. That would kind of be the old world. Instead, you would do this thing where you do ref.unsafe.set to. And so far, we've just kind of cabined these off in a little bit of a different like namespace. We haven't really done anything to address that idea of getting the compiler to help us. But then what we'll do is for these methods, we require this implicit unsafe thing. And if you spent some time like with Scala 3, this is really an example of that idea of capabilities that Odersky talks about. So like he talks about wanting to be able to model functions that can throw exceptions and having that reflect in their types in a way that shows that they can throw exceptions and lets you handle those exceptions, but maybe doesn't require you to always go through like an either or a try type data type and kind of make everything a for comprehension. And so his version of this would be like a implicit can throw. And it would say, well, you need the capability to throw exceptions to do this thing. Here, we're using a different variant of this, of we're saying you need the capability to do something unsafe to do this thing. And then in ZIO, we have this operator called unsafe, which basically says, okay, in this region, I want to be able to do something unsafely. So if I wanted to like set my ref, then to get it to compile, I need to do it inside one of these code blocks.
Mhm.
And so then when you're doing code reviews, you can look for usages of these. And what can make this even nicer is you can think of this unsafe as kind of providing this capability at the end of the world. And ideally, you actually want to use this very infrequently. And what you want to do is you more want to propagate that unsafety up, which implicits or givens in Scala 3 really let you do very nicely. So you could imagine maybe in this unsafe API, we have another method get here. And this is going to return an A. And it's also, maybe we'll put the parentheses here to indicate that it's side effecting. And we'll also require the unsafe capability for this. And so then let's say I want to go and I want to do something like I want to define a get and set method. That's going to take like a ref. That's a ref of a, or actually, let me maybe make this update. That's going to take a ref, and then it's going to take one of these functions, A to A. I'm going to use that same currying trick that Kit was talking about earlier. And this one, let's say I'm kind of doing the unsafe version right now. So this is going to return unit. And so what I might do is I might then say something like, and we're going to ignore the fact that this is not going to be concurrency safe right now, just to kind of demonstrate this, because we could use the compare and set, but I think we won't do that in the interest of time here. But we could say something like old value equals ref.unsafe.get. And then we could say ref.unsafe.set f of old value. And if we do this, I think since I'm kind of in the guest session, I'm not sure I'm getting the same error message, at least on my screen. But I think what we're going to see here is we get this error message that basically says we don't have the capability to do unsafe things yet.
Yep.
And so,
on that, so it shows, yeah. So could not find implicit.
oh, perfect.
Yes, exactly.
And so what that pushes us to do is like, so now this is where the compiler is helping us out, because the compiler is saying like, hey, you're doing this thing. There's unsafe stuff inside of here. And it's essentially forcing you to either say, hey, I know there's unsafe stuff. I'm okay with it. In which case you do this unsafe, not unsafe here. Or, you know what? You're right, compiler. This is an unsafe thing. I need to be careful about this. And then you put the implicit, oops, unsafe up here. And now maybe I name this unsafe update, or I put this in its own unsafe API for whatever it is. But now the compiler is helping me and saying like, hey, this thing was unsafe. So if you're doing unsafe stuff inside of it and you don't kind of know that it's okay, then this thing itself is potentially unsafe. And then that's also going to propagate up where if somewhere else you are calling unsafe update, it's going to say like, hey, this is an unsafe thing to do. And wherever you kind of get to it, big enough part of code where you say like, okay, I know I'm doing some unsafe stuff, but I'm okay with it. And maybe I'm okay with it because like this unsafe update, I'm actually doing within like a ZIO succeed that's specifically designed to handle this. And so maybe that's why I'm okay. And I'm going to do the unsafe inside of this. And at Scala 3, there's actually some special functionality that will like eliminate that unsafety if you're using ZIO succeed, as long as you're using kind of the right operators. But that's the overall idea here. And I think one thing you can take away from it is that you can kind of use your own version of this technique. So if we go to this unsafe thing, see, I'm not sure if yeah, perfect. Thank you. You can see it's like a really, really simple thing because the unsafe doesn't actually do anything. It's just this like pure marker here. And so all we do is we create this like private version of like this like sentinel value. And then we say, if you have this unsafe thing, we're just going to give it the sentinel value. So one thing you can take away from this is if you ever have your own case of you've got some API and you have kind of the higher level API and the lower level API, and you want to demarcate those two and separate them, you could create your own data type like this. Or if you're in the ZIO ecosystem, I think one of the nice things about this unsafe data type is it can hopefully be a little bit of like a common language for this type of unsafe functionality, where this is just a data type that's in ZIO, and you can make your own operators that require this unsafe capability. So if you're doing something that is very low level and is side affecting, you can use this too, and it'll naturally integrate with everyone else who's using this in the ZIO ecosystem. So I think it's kind of a cool example of a different use of implicits to provide more safety to an API. And I think probably something we'll be seeing more of in different ways in Scala 3 of it is very much the direction that like Marnodowski is pushing with can throw and these other capabilities, and really what he was kind of why he created context functions, or what were previously called implicit function types.
Amazing. Okay. Well, I think that covers most of the tricks of ZIO. We had one last little section about just rambling on companion practices, but I want to save that for another time. It's definitely less. There's not really much code there, yeah. In 2 words, put constructors and high rarity combinators on your companion objects, and put everything else on the traits or classes themselves. But we'll look at that more some other time. Yeah, hopefully that was fun. Some little fancy tricks. I don't think, ZIO invented any of these, or not all of them, certainly. They're sort of just been sitting and in there in different open source libraries in different sort of inchoate forms. And it took a while to sort of figure them all out myself, because they're not really taught in, many places. They're kind of advanced and weird and really only concern library authors. But I don't know, I find them all pretty interesting. So we wanted to take a day to just kind of document for future generations some patterns that are useful for doing these little, API niceties, API polish. So yeah, hopefully that was interesting. And we'll see you, I guess, next week. Yeah, we're going to talk about replacing Akka.
Good, yeah.
Cool. Well, any questions? Any lingering thoughts? Are we good?
I think we're good. Thank you so much, everyone.
Ta-ta. Have a good weekend, everyone.